Thanks for the invitation. Yeah, my only regret is not being able to visit Montreal in person. It's one of my favorite cities, and I always love coming here. So I hope before very long I will be able to come in person. But yeah, as it is, just online. So yeah, I'm going to be talking about some work I've been engaged with. The origins of this actually were in some conversations in Banff almost exactly 4 years ago with Amichai Hanany when we were in Banff for a program on moduli spaces. So it took a while for things to germinate, but yeah, we have written 2 papers, and we're trying to complete a 3rd at the moment. So these are my collaborators. Here are the two completed papers. The first one is to appear in Advances in Theoretical and Mathematical Physics, and the second one just appeared a few weeks ago in JHEP, actually. So, as the title suggests, this is a little bit more towards the physics end of the spectrum than I usually am. Obviously, I've come at this from the mathematical end, hyperkähler geometry in particular. I certainly don't pretend to understand all of the physical background to these questions. And I should probably also mention, yeah, because we're using quite a lot of techniques from physics, sometimes the statements may be a little bit more imprecise than usual in a math talk. I mean, there are certain techniques where they're not sometimes stated as theorems, not totally clear exactly under how widely these techniques are applicable. But I hope you'll indulge me in this during this talk. Okay, so what's the background? This is part of a story of one of these dualities, which is so exciting in mathematical physics. It's not exactly mirror symmetry, something a bit different. It's the duality, people often call it symplectic duality, which physically is the duality between 2 different branches of a certain class of physical theories, the so-called Coulomb branch and the Higgs branch. For our purposes, we're going to be thinking of this as a duality between certain pairs of holomorphic symplectic, in fact, in practice, actually always hyperkähler spaces, but possibly with certain singularities, typically affine varieties. They have a bit of extra structure. I think the sort of original form of a duality was really for hyperkähler varieties with a conical structure. You often consider sort of little deformations of those where the conical singularity is smoothed away to a smooth affine variety. And that deformation typically breaks down an SU2 action that rotates the Kähler structures to a circle action that rotates the Kähler structures. So there is a little bit of extra data. These are not completely arbitrary hyperkähler varieties. So it's a duality which comes from physics. Unlike sort of the classical 3D mirror symmetry, the dimension can change. The dimension of the Coulomb branch and the Higgs branch can be different. In fact, typically they are. I'll say a bit more about that later. There are various points about how these are related, and one in particular, which is going to be important, is the deformation parameters on one side of a duality are supposed to correspond to the parameters in the Cartan algebra of a symmetry group on the other side. So the physical terminology, usually on the Higgs branch, which typically, though not always, arises as a hyperkähler quotient, the deformation parameters of what we would call the essentially level set of the moment map. In the physics language, they would be Fi parameters, Phi Atelier parameters. On the other side, on the Coulomb branch, which is typically more mysterious to mathematicians, the deformation parameters are referred to as the mass parameters. But this is one particular way in which a duality is supposed to work. So let me begin by saying a bit about the Arbelian case, which is quite well understood now by the work of many authors. So the Arbelian case, really thinking of hypertoric varieties, as I said, the Higgs branch typically is given as a hyperkähler quotient, though not always. So the case of hypertorics, of course, are where we're looking at hyperkähler quotients of flat d-dimensional quaternionic space by some subtorus of the torus of symmetries TD. The subtorus is usually viewed by an exact, in terms of an exact sequence like that. So the subtorus has a real dimension d minus n. So when we hyperkähler reduce, we get a hyperkähler quotient of real dimension 4n. And of course, there is a residual action of the quotient torus Tn, which is Td modulo the torus n that we've quotiented out by. So this is, of course, a maximal rank hyperkähler action. We have a hyperkähler manifold of real dimension 4n, the quaternionic dimension n, with a Tn action. So this, of course, is intended to be reminiscent of the classical case of toric varieties, where you have a Kähler manifold, Kähler variety of complex dimension n with a Tn action. Now, of course, in the case of classical toric varieties, that Tn action, essentially the moment map for that, will project it with toral fibers onto some polytope or polyhedron, compact polytope if it's a compact manifold, and basically just about everything reduces to sort of the combinatorial convex geometry of the polytope. Now, in the hyperkähler case, again, yeah, I mean, in principle, really everything can be expressed in terms of combinatorial convex geometry. It's not quite the geometry of a polytope now, it's really more sort of hyperplane arrangements or arrangements of affine subspaces in R3n. Essentially, that's because the basic hyperkähler moment maps are typically surjective rather than onto a polytope. They're sort of different, involving differences of squares rather than sums of squares. So how does this fit into the duality picture? Well, as though we have a Tn action, so n parameters for the symmetry, and how many deformation parameters do we have? Well, we're hyperkähler reducing by d minus n dimensional torus, so we have basically d minus n deformation parameters if we deform in a way so as to preserve the circle action. Let's look a little bit more closely at how the torus is defined. Essentially, we pass to the Lie algebra level, and just taking the Lie algebra version of that exact sequence, the Lie algebra of a torus is defined as the kernel of some linear map beta from Rd onto Rn, which we can encode basically just by telling you where beta sends the standard basis vectors of Rd. So it's encoded basically by these d vectors u1 through ud in Rn, and that's sort of the start of the combinatorial convex geometry picture here. So we have d vectors in Rn. So say in the classical toric case, these would essentially with normal vectors to the face of the polytope. Here the situation is slightly more complicated, but yeah. What does symplectic duality do in this picture? Because the motivation for this was considering what happens with symplectic duality. Roughly speaking, the duality just swaps the roles of the subtorus and the quotient torus. And a more precise statement is we would dualize that exact sequence of tori. So then the role of n would be played by Tn dual, and the role of Tn would be played by n dual. So that's consistent with what we said earlier. I can just scroll down a little bit. On the one side, we have the d minus n deformation parameters in a Tn symmetry. When we dualize, of course, as I say, the roles of n and Tn have essentially been swapped. So we have n deformation parameters and d minus n symmetry parameters. So that's an example of what I was saying, that under symplectic duality, the deformation parameters and the symmetry parameters get swapped. Well, you can actually push that much further. We started off, as I say, encoding the subtorus basically in terms of the collection of d vectors in Rn. When we dualize, of course, we're getting d vectors in Rd minus n, and actually very very nicely, this actually turns out to be a classical duality in combinatorial convex geometry that's called Gale duality, and I guess that's even a duality in linear programming, actually. Essentially, the d minus n dimensional space is basically the set of dependency relations for u1 through ud. That's where the d minus n dimensional space comes in. So it's a very nice interpretation of this in terms of some quite classical combinatorial convex geometry, and people like Braden, Licata, Proudfoot, Webster who have pushed this idea a lot further. I think we have a fairly complete understanding now of duality in this Arbelian case. What about the non-Arbelian case? Well, this is this is sort of leading us to quiver varieties, at least an important class of examples, and this is rather less well understood.
Andrew, and sorry, could you speak a little bit louder?
Yes, I'm sorry. Yeah. Okay. Let me turn the microphone level up a little bit. Yeah, well, so we'll take the Higgs branch to be a quiver variety, a hyperkähler quotient of some big linear space by a compact group. So the idea, sort of stemming, for example, from work of Nakajima and his collaborators, and Finkelberg, Braverman, etc., is the Coulomb branch is expected to be birational to the cotangent bundle of a dual complexified torus of K modulo the Weil group. So that should give us a dimensional relation. The quaternionic dimension of the Coulomb branch should be the rank of K, the group by which we're quotienting to get the Higgs branch. If we took complex dimensions, of course, it'd be a factor of 2, real dimensions a factor of 4. There's a nice sort of physical interpretation of this, which I certainly wouldn't pretend to fully understand, but the statement you usually see here is that the classical model for the Coulomb branch would be this essentially flat space, this cotangent bundle of the flat torus modulo the Weil group on the nose. The birational transformations correspond to quantum corrections to that classical picture. So it's a rather a nice sort of physical interpretation of the geometry there. Now that, of course, in itself doesn't go perhaps all that far to giving you the precise description of the Coulomb branch, but that's something to keep in mind. So the idea, in fact, which in fact follows very, very nicely from Nakajima's interpretation of his definition of the Coulomb branch, is that this should sort of basically fiber over the Cartan algebra modulo the Weil group. There should be some kind of integrable system picture there. Great. So what are we looking at in this talk? Looking at a sort of particular class of spaces that I've been involved in for several years, working with Andrew Swan and Francis Kirwan and others. The so-called hyperkähler implosions or complex symplectic implosions. So these are motivated by the classical symplectic implosion due to Victor Gilliman, Lisa Jeffrey, Reyes Samar. They have some quite nice links with geometric representation theory. So what is the hyperkähler implosion? Well, it's supposed to be at least a complex symplectic space, and hopefully even in some suitably stratified sense, a hyperkähler space, with a complex symplectic action of K complexified across the maximal torus T complexified, actually a hyperkähler action of the compact group K cross T, and the dimension actually is the dimension of that. It's the dimension plus the rank. And one way of viewing this is that it's sort of a master space. It has these two commuting actions, the K action and the T action. And the idea is that if you reduce by the T action, hyperkähler reduced by the T action, then it should give you the costant varieties that are the fibers of the costant morphism. So if you like, basically these are the varieties we get by fixing the values of all invariant polynomials on the Lie algebra. In particular, the reduction at level 0 should give you the nilpotent cone. And of course, the dimensions work out there because the dimension of the nilpotent cone is the dimension of the group minus the rank. So the implosion just is a sort of master space sitting above all these constant varieties with dimension of the group plus the rank. So this is sort of, say, by analogy with the universal symplectic implosion of Coulomb and Jeffrey-Simard, because then the torus reductions there will just give you the various co-adjoint orbits for the compact group. Now, obviously, in the complex symplectic case, of course, life is a little more complicated because the complex co-adjoint orbits are not necessarily closed. So the correct picture is we get these constant varieties, which in general are unions of complex co-adjoint orbits. In fact, they're closures of the regular complex co-adjoint orbits, but then there are typically, in some cases, there are other lower dimensional complex co-adjoint orbits coming as lower strata in the closure. So this is a sort of nice analog of the Coulomb and Jeffrey-Simard picture of symplectic implosion, but there are certain new features that come in. So we reduce by the T action, and then we have the residual K action, which is the action on the nilpotent cone or the other constant varieties. We can say a little bit more about these guys. They arise, and this was sort of one of our original motivations, as non-reductive geometric invariant theory quotients. I'm sorry. So this is, of course, is something that Francis has been pioneering for several years now. They can be viewed, perhaps the nicest way to think about them is as follows. The classical, the symplectic implosion, as I said, has a real symplectic description, but it also has a nice non-reductive GIT description as the quotient of the complex group by the maximal unipotent U in the GIT sense. Now, because U is non-reductive, it's not automatic, of course, that that quotient makes sense as a variety. It's not automatic that the algebra of invariance is finitely generated. Fortunately, in that case, and also in the case we're dealing with, that is true. So these do actually exist as varieties. So the classical symplectic implosion could be viewed as the GIT quotient of Kc, which could be viewed as T star K by the maximal unipotent U. So what should the hyperkähler analog of that be? Well, clearly what we should be starting with is not T star K, but T star Kc, which by work of Kronheimer going back to the 80s, we know is actually hyperkähler with a K cross K hyperkähler action. And then we take the complex symplectic quotient of that in the GIT sense by the maximal unipotent, i.e. we take the zero level set of the moment map. That means basically we cut down the dual of the algebra to the annihilator of the algebra of the maximal unipotent, and then we mod out by the maximal unipotent put in the GIT sense. So if you like, the original K cross K or Kc cross Kc action on the cotangent bundle has been broken, the right Kc has been broken down to the torus, which is the Borel modulo U. So the left Kc action survives, but the right Kc action has been broken down to the torus. So that's correct, as we have here. So this all sort of works out rather nicely, fits in very nicely with the theory of the Springer resolution, for example. And as I say, it's actually now a general theorem by Victor Ginsburg and Simon Riesch that the non-reductive quotient that I have here is well defined as a variety. We do have finite generation for the ring of invariance. Great, so that's sort of a rather high level sort of description of the implosion. In the USUN case, fortunately, we have a more down-to-earth description, and that's sort of where the symplectic duality comes in. So we do actually have a quiver description in the SUN case of the implosion. So it turns out to be like nice finite dimensional construction. It is actually a hyperkähler quotient of a linear space at level 0. So because it's at level 0, we expect a kind of conical structure and the SU2 action rotating the complex structures. So this should fit into the duality picture, just as many other examples of quiver varieties do. So the question we got thinking about when we were in Banff was what might the dual look like if this is the Higgs branch? What is the Coulomb branch? So we've been exploring some interesting spaces which are nice candidates for the Coulomb branch of the implosion. Certainly the various numerical checks one can do seem to check out. So they seem to mimic the desired properties of the Coulomb branch of the hyperkähler quotient of the hyperkähler implosion. So we now have to motivate this, to motivate our construction of the candidates for the Coulomb branch, we have to make a little detour into the physics of symplectic duality. So let me just go back to the first slide just for a second. Remember what we said was under the duality, the deformation parameters are supposed to get swapped with the Cartan algebra of the symmetry group. So what we're going to do now is a refinement of this picture, which the string theorists have been working out. So suppose we're looking at a hyperkähler space, a Higgs branch arising as a quiver variety. So, the picture is we have this sort of diagram with this graph. The vertices are labeled, but in the simplest case, labeled by unitary groups. And then the edges, those are the groups by which we hyperkähler reduce. And then the edges, of course, these are labeled by flat quaternionic spaces. Basically, if you have an edge linking a node with label Ni and a node with label Nj, then the space in the edge will be HNI Nj, which perhaps more nicely we could think of Hom CNI CNJ plus Hom CNJ CNI, and then the unitary groups act in the natural sense. Okay, so these are the gauge nodes, the nodes at which we're actually performing the hyperkähler reduction. You may also have nodes where we've turned off the unitary group, where we're not reducing by the unitary group of that node. Those are typically denoted by square boxes and called flavor nodes. I'll probably, if I can make the whiteboard work, I'll do a couple of examples of this. The interesting feature for our point of view from the duality is the notion of balance. So this is something that comes out of the physics. But the balance is an integer that we can associate to each node in our quiver diagram. And it's, let's say, minus twice the dimension at that node, plus the sum of the dimensions over the adjacent nodes. And from a physical point of view, for a sort of nice theory that you can calculate with, we don't want the balance to be too negative. We'd like the balance to be at least -1 in all cases, preferably non-negative. And the nodes where the balance is actually 0, the ones we call the balance nodes, these are very significant for the predictions under symplectic duality, because the statement is, and this is something coming out of the physics, is that the balance nodes should give you the Dynkin diagram of the semi-simple part of the symmetry group of the Coulomb branch, or at least a subgroup of the symmetry group of the Coulomb branch. There are actually examples where it's a proper subgroup, but usually they're actually the same. So this refines the statement at the beginning. As I said before, deformation parameters in the Higgs branch should give you Cartan algebra of the symmetry group of the Coulomb branch. Now, what does that mean for a unitary quiver? Where are our deformation parameters coming from? Well, we're hyperkähler reducing, so the deformation parameters come from the center of the group by which we're hyperkähler reducing. So each node each unitary group UN will have a one-dimensional center. So each node should give us a deformation parameter, and hence that should give us a parameter for the Cartan algebra over in the dual. So what this rule is telling you is how to thicken up the Cartan algebra of the dual to an actual semi-simple or reductive group. So it is refining the statement I had right at the beginning. The statement I had right at the beginning only tells you about the Cartan algebra of a symmetry group. This, using the balancing conditioning, is telling you how the Cartan algebra thickens
Andrew,
up.
we have a question. Hang on.
Sure. What's the
Hi,
question?
Andrew. Hi, this is Lorenzo. I want to ask, so you're saying sort of this, so is there a quick reason to say why the node must be balanced to carry a deformation parameter for the quiver variety?
No, I mean, all the nodes will induce a deformation parameter because, as I say, the deformation parameters just come from the center of the group. So each node will give you a one deformation parameter. The new feature, and this, as I say, is coming from physical considerations, is the balanced nodes will then actually not just give you Arbelian symmetries over in the dual, they will tell you how that Arbelian symmetry thickens up to a semi-simple or reductive group.
But that should be, I mean, it's not, I mean, on the side of the deformation, it's mathematics, right? So it should be related to this Namikawa theory of Poisson deformations or something.
Quite possibly, yes. I mean, yeah. Okay. Yeah. So that's the so this is the balancing condition that we use to make predictions about what's happening over on the Coulomb branch. So let's see. I think I will now, at this point, I will try and use the whiteboard just for a few minutes to illustrate a couple of examples. Let's see if this works. Okay, is this visible? Is the whiteboard visible?
You see the whiteboard?
Yeah, okay. So let's think of a couple of examples. You'll just excuse my handwriting. Let's think of the example of the nilpotent cone. So just for SUN. So what have we got? This goes back to a work of Andrew and Piotr Kobach, and well, yeah. So what's the quiver we have of nilpotent cone for SUN? We'd have a quiver like that. So the circle nodes, the gauge nodes, these are the nodes at which we perform the reduction by the unitary groups of the given rank. And then the box at the end, that's a flavor node, which we do not reduce. So so that is giving us a residual UN. Well, what is the balancing condition? The balancing condition would just say that twice your dimension is the sum of the adjacent dimensions. And we see, of course, all the gauge nodes are balanced, aren't they? Because at each stage, because of the way the ranks go, actually all those gauge nodes are actually balanced. So actually, whoops. Yeah, this is the so these guys will actually form a balanced configuration. So over on the Coulomb branch, we'll have an SUN action. And that actually is correct, but in fact, nilpotent cone is actually its own dual under symplectic duality, in fact. So that's correct. Let me think of another example. So this is sort of basically giving us Calabi, or the singular limit of Calabi, which would be a closure of a closure of a minimum nilpotent orbit. So that would correspond to a quiver diagram like this. So we have a one-dimensional node, and then there's the flavor node, which we're not reducing. So if you like, this is just the sort of fact that we can get Calabi by hyperkähler reducing by a U1 corresponding to that gauge node, or the singular limit of Calabi, of course, depending on which level we reduce that. So what can we say? Well, if D is not equal to 2, then the gauge node is unbalanced. So that just gives us, if you like, an Arbelian part. The unbalanced nodes, as I say, they'll give you a deformation parameter, so they'll give you one parameter in the Cartan algebra over on the dual, but that will now just be a pure Arbelian bit. So that will just give us an Arbelian symmetry over in the dual. On the other hand, D equal 2, we can see is special, because then this is actually balanced. So we would then get A1, so we'd get an SU2 or a U1. And that actually, of course, that actually is correct, isn't it? Because what is the what's the dual? Well, this, of course, actually falls into the Arbelian story that we talked about early on in this talk. It's an example of a hypertoric. And what would the dual be? Well, we are essentially taking the complementary torus, aren't we? We're taking this guy. So this is basically, this is the multi-instanton spaces. We're getting this, I guess, isn't it? Or the deformations. So we'd be getting these multi-instanton spaces, which generically, of course, have a U1 action, but of course, in the D equal 2 case, Higuchi-Hansen actually has a bigger action. It has an SU, well, actually, has an SU2 action. So those are examples of this kind of yoga balance nodes. So let's now. Let's now go back to here. I hope the PDFs are now visible again.
Yeah.
Yeah. Okay. Is the size okay?
Yeah.
Yeah. Okay. Good. Yeah, we were having a little bit of trouble with the sizing, but yeah. So this is the yoga coming from the physics about making some predictions about the Coulomb branches. Okay, so what about our concrete problem? We're trying to find some spaces that are candidates for the Coulomb branch of the SUN hyperkähler implosion. So what do we want? Well, we need an SUN action, and we also need an action of its maximal torus. So I should say, actually, there's a slight subtlety about what I said. You sometimes have, and this is actually sort of quite familiar with hyperkähler quotients, you sometimes find there's a sort of circle action, which, well, the physicists say decouples. I mean, from our point of view, it would be acting ineffectively. There'd be a circle action acting trivially, which you have to drop. So that's something that comes up in this. But we can actually produce a class of spaces that have this kind of behavior. And the idea is we actually start with our old friend that we saw a few minutes ago, the quiver for the nilpotent cones. Remember, that was just a chain of length n-1 of balanced nodes. And then we have this n-dimensional flavor node at the end. So if we excise that flavor node at the end, well, that would, of course, immediately unbalance the adjacent node. It would only have n-2 next to it, and you'd need, we need to rebalance it. So how do we rebalance it? Well, we could replace the n-dimensional flavor node with a bouquet of n one-dimensional nodes emanating from that. So we have essentially a chain of length n-1, and then at the end, out of the n-1 dimensional node, for now n one-dimensional nodes attached to that by legs. Okay, so that would keep it balanced. So the balanced nodes are now the same as they were before. These are the n-1 gauge nodes, which would form an an-1 diagram, and that would yield SUN symmetry in the dual. The unbalanced nodes, they would, as I mentioned in the earlier example, they would just yield an Arbelian symmetry, but one of those actually decouples, so we get a Tn-1 symmetry after decoupling. So this would produce a space, this Bourget quiver would be the Higgs branch, whose Coulomb branch would have the correct symmetry group. So this is a start. So there are some we'd like to do some more checks on this. What about the n=3 example? Okay. So perhaps this is a place where it would be good to go back to the whiteboard for a second. Yeah, this is a case where it would be slightly easier to do things on a on a physical screen. Yeah. So what have we got? As I said, our starting point was the quiver for the nilpotent cone, but we're now erasing that guy. We're erasing that flavor node. So then to keep that n-1 node balanced, we need n one-dimensional Arbelian nodes attached to it. So this is, as I say, well, this is what we call a bouquet. There's one special case, though. Let's go back. So if n=3, so in that case, and uniquely in that case, actually the bouquet nodes, the one-dimensional nodes that we've attached as the bouquet, these are also balanced because twice m equals the dimension of the adjacent nodes. So in this case, actually the symmetry group over on the Coulomb branch should enlarge. So what is this? This is an affine D4 diagram. As I say, one sort of node essentially decouples. So that should give us over on the Coulomb branch, that means we should get an SO8 symmetry. And that actually is correct because the implosion in the n=3 case, we actually is actually the Swan bundle of the Grassmannian of oriented four planes in R8. So it's a Grassmannian of the Wolf space SO8 over SO4 cross SO4. So in fact, it will have an SO8 symmetry. The symmetry group gets enhanced, as they say in this case. So that's actually a nice little test, this particular example, that something is working. Right, so let's go back to the diagram. Yeah, so in the n=3 case, this is just a restatement of what I did on the whiteboard. This is correct because this does predict the symmetry enhancement to SO8. Well, there are further checks one can do. So the string theorists have got quite an elaborate set of calculational techniques, in particular for calculating the Hilbert series of the affine varieties that are the Coulomb branches, and also the Hilbert series for the hyperkähler quotients of the Coulomb branches. So we can check that the dimension as well as the group action works out okay. Remember, quite early on, I mentioned the Nakajima viewpoint gives you a relation between the rank of the group by which you're hyperkähler reducing to get your Higgs branch and the dimension of the Coulomb branch because of this birational equivalence. So we can just check that that does work out okay. In this case, because the Bourget quiver, that's the Higgs branch, is the quotient of the effective action of that group with rank given by that, and the complex dimension of the implosion is indeed twice that, so that's consistent with Nakajima. Moreover, a sort of deeper check is, say, the implosion. It's supposed to be a master space. It's got an action of a group, but it's also got an action of the maximal torus. And if we reduce by the maximal torus, if we symplectically reduce by the maximal torus, it's supposed to yield the fibers of the constant morphism, the constant varieties. Particular reduction at 0 is supposed to give you a nilpotent cone. So that's a deeper check, and that's one that one can do, as I say, using the computational techniques that have been developed by the string theorists, and that works out fine for these examples, which that's a more substantial check. So certainly we've got an interesting class of examples, which certainly seem to be mimicking the correct behavior of what we would expect for the Coulomb branches of the implosion spaces. So perhaps in the last few minutes, let me sort of mention some more recent work. So we've been looking at unitary quivers. Well, you can try and play a similar game for orthosymplectic quivers. So the interpretation of the implosion space as a quiver variety doesn't work now, but just the variety, the GIT quotient, the non-reductive GIT quotient of the cotangent bundle of the group by the maximum unipotent, that still makes sense as a variety. So we can take that as our definition of the implosion in this case. So we can still hope to find something that has the correct properties for the Coulomb branch. So we can actually play a similar game to what we had before. We can start with the quiver description of the nilpotent cone, but now be an orthosymplectic quiver. This again is in Kovacs 1. The nodes alternate between orthogonal and symplectic groups. And you can try the same trick we did before. We can excise the flavor node at the top. So in the DN case, that's the simplest. We'd excise the SO2N flavor node. Then that would leave exposed a symplectic node, which now has to be rebalanced. And we can do that by replacing it with a bouquet of N Arbelian SO2 nodes. Now the balancing conditions change. You have to modify the balancing conditions in the orthogonal case. Basically, for orthogonal symplectic groups, the equations for the balancing condition shift by +2 or -2. And also the way in which you predict the symmetry group in the Coulomb branch from the graph of balanced nodes changes clearly. So I won't go into the details about how that changes. But this does actually give us, this procedure does give us the correct dimension symmetry group. And again, one can check that over on the Coulomb branch, when you're reducing by the maximal torus, you're getting to nilpotent cone as expected. That's for the, as I say, for the DN case. Similar game actually works in the BN case. There we start with the quiver diagram for the nilpotent cone of the Langland's dual of the symplectic group. We excise the symplectic node. Then we have the sort of tricky question of how to rebalance the exposed orthogonal node. In fact, actually it works out that just balancing that by unitary nodes actually works in this case. And again, checks can be made. More recently, the paper we're trying to conclude at the moment is about partial implosion. So perhaps let me just mention that very briefly. So where are we? Yes, if I go back to my non-reductive GIT description of the implosion, that's essentially the complex symplectic quotient in the GIT sense of the Cronheim space, a complex cotangent bundle by the maximal unipotent. So the maximal unipotent, of course, we could view as the commutator of the Borel. But of course, you could say, well, why not replace the Borel by a general parabolic? So then the U would be replaced by the unipotent associated parabolic. And instead of breaking the symmetry from Kc cross Kc to Kc cross Tc, we would now break it to Kc cross the Levy group. Okay. So in the symplectic implosion, that picture has actually been pretty well worked out and sort of gives you what you expect. Now in the hyperkähler implosion, we actually know much less. In fact, we don't yet have a proof that this the analogous partial implosion is well defined as a variety. We don't have a proof of finite generation yet. However, it actually is interesting that for some cases, at least the cases where we've been able to work out, the Coulomb branch, the duality picture, does actually seem to make some sense. And in particular, for SUN, the natural thing to do is to refine the Bourget picture. So we now have, we have all these legs emanating out of the top node, but of course now we allow various lengths. So rather than just having n length 1 legs, as we did before, we have the legs of various lengths giving you a partition, so corresponding to a choice of parabolics. So that's a very natural choice to make. The sort of string theory calculations now get very much more complicated, but in the cases where my collaborators have managed to perform the calculations, this does actually seem to give the correct answer. The various computational checks that one wants to make do actually work out. So there does seem to be something interesting going on there. So that's work in progress on the partial implosions. Okay, so as I say, this was a little bit more towards the physics end of the spectrum than usual, but I think there is some very interesting stuff going on here. I've always thought, in fact, that hyperkähler geometers should get interested in what the string theorists are doing with their quiver diagrams and their computational techniques, and there does seem to be quite an interesting story emerging here. So thank you for your time.
Thank you. Any questions for Andrew?
Hello, Andrew. This is Vicente. I would be interested knowing about the hyperkähler metrics. So can you say something more in detail about these metrics? So are there cases where you can prove they are complete?
Right. So so it's only what can we say? For general groups, all we really know is that this non-reductive complex symplectic quotient exists as a variety, which should be holomorphic symplectic, at least in a suitable stratified sense. Now, what we expect is that it's actually hyperkähler again in a suitably stratified sense. But I should emphasize these spaces are almost always singular. And actually that's true even for the more classical symplectic implosion, but except for SU2 or products of SU2s, even the symplectic implosions have singularities. Even for SU3, there's a conical singularity. So you would only expect, as I say, a rather singular hyperkähler structure. You certainly wouldn't expect a complete and in a way that makes sense, because these things are kind of intimately related to nilpotent cones. As I said, we're getting the nilpotent cone as the toral reduction at level 0, and the nilpotent cone, of course, that's a pretty singular, that's a stratified space, and the various strata, of course, going back to Peter Kronheimer, these have hyperkähler metrics, but definitely incomplete ones. So you don't expect, from that point of view, the hyperkähler structure is, so you expect to be pretty singular. I agree.
Are there some, excuse me, are there some quantum corrections expected which could remove these singularities?
Right. That's a very good question. I don't know, but I mean, the way to think of that might be through symplectic duality, because I suppose the moral of this is that the Coulomb branch, I mean, once you get away from SUN, one thing I didn't mention, but I probably should have done, was that, as I say, we don't have a quiver description for the original implosion, but there are quiver descriptions for these things that are behaving as we expect the Coulomb branches to behave. So this is sort of one of these cases. I think the physicists call this, you have a Lagrangian theory on one side and the non-Lagrangian one on the other. In that case, the Coulomb branch seems to be, in a strange way, more accessible, sort of the opposite from what one usually expects. So it might be actually that symplectic duality might be the right way to think about resolving singularities or whatever. Yeah.
Thank you very much.
Any other questions for Andrew? Okay, well then let's thank Andrew again. So the talks resume at 2 o'clock, but I remind everyone that there's a poster session at 1:30, and all the participants should have gotten an email about how to log into the poster session. Thanks.
So Andrew, a speculative question. Is there some extension of this theory to that will involve the diagrams from Catmoody algebras?
Right, that's interesting. So of course we have seen an example of this, with the affine D4 came up. Yeah. I think, as I say, this is sort of part of the physics yoga that I'm sort of unsure of. I think when the Catmoody algebras come up, what that indicates is basically the kind of phenomenon that we had here, where essentially there's a decoupling going on, as the physicist would say, that is one of these nodes actually is sort of a fake, and that you now have to cut it down to the classical Lincoln diagram, giving you the SOH symmetry. But as I say, as I mentioned at the beginning, it's never quite clear from these procedures exactly what kind of conditions you need, what kind of assumptions you need to make for the various rules to hold. And in particular, as I say, once you get into quivers that are bad, where we have balance, some nodes with balance less than -1, I suspect a lot of these things now break down. Certainly a lot of the physics calculations, you now get divergent series when you try to apply your formulae. So I think one has to be quite careful with applying this rule, and in particular, you probably don't want to apply it where negative balance comes in, or balance less than -1. That's actually something I have sort of talked with people about a bit, that there seems to be some feeling that having bad quivers should somehow be related to the variety defined by the quiver not being a complete intersection or something like that. It would be very interesting actually to get a more algebraic geometric interpretation of the bad quiver, what badness means for quivers. You sometimes see papers by string theorists talking about good, bad, the good, the bad, and the ugly in quivers. So good means non-negative balance, and ugly means balance equal to -1, and bad means balance less than -1. So yeah, I think if you had sort of badly unbalanced quivers, then what I said probably may not be applicable. And in particular, I mean, I didn't mention this, but one of the Hilbert series calculations that they're doing, they're mostly using this very nice monopole formula due to Alchai, one of my collaborators, and Cremonesi and Zeffironi, and that's extremely nice actually, because physically that means you're counting monopole operators with certain kinds of singularities. You're which physically means you're counting the chiral ring, which is how they interpret the coordinate ring. Yeah. But actually, that's very nice because if you're looking at the kind of singularity that your monopole operator has, this will have a nicely theoretic interpretation. So basically, the monopole formula involves some various summations, but one of them is a sum over the weight lattice of a certain group. Okay. And for the bad quivers, their calculations tend to give you sort of divergent answers. So yeah, so getting back to your original point, my impression is that at least in sort of theories that are well behaved, the affine Dynkin diagrams do play a role, but it's usually one like the example I saw. It indicates there's some kind of decoupling going on. So essentially you have to remove a node and get back to a classical Dynkin diagram. But yeah, I think there's a lot that's not, a lot here that's not sort of fully worked out from a mathematical point of view. But actually, I mean, there is and it's probably, I wouldn't know where to start with this, but of course, I mean, Nakajima and his collaborators relatively recently, they do have a proposal which seems to work out perfectly for what the Coulomb branch should be, but it's very complicated. You start with your Higgs branch, so your quaternionic representation of your group G. And then what you do is you start with the affine Grassmannian, this infinite dimensional object. So Laurent series, finite Laurent series valued in G modulo Taylor series valued in G. We could interpret this, I guess, as bundles over the formal disk with the trivialization over the function disk. Then you soup that up a bit using your quaternionic representation. We associate some new space to that. This has an action of this infinite dimensional group, this kind of loop group. You then take an equivariant homology of this infinite dimensional space with respect to this infinite dimensional group, and then spec of that is supposed to be the Coulomb branch. So in principle, some of these things probably should be worked out from Nakajima's proposal. Now, whether that's feasible, I'm not sure, but yeah. But, and actually you do see from Nakajima's proposal, you do see very nicely the fact that the Coulomb branch is expected to fiber over the Cartan algebra modulo the var group as a kind of integrable system, because that Cartan algebra modulo the var group is basically spec of the equivariant homology of a point. So actually that picture drops out extremely nicely from Nakajima's results. So yeah.